Morning.
So, when we got together on Thursday, I guess it was, the one thing you'll notice about the entire semester, I'm always going to be confused on what day it is, because in my mind they all just end in the letter Y, and that's about it. So I realized today's Monday. I hope you all had a good weekend. As I told you on Thursday, I was going to start the course off by showing you the end. And I don't mean the end in terms of time, I mean the end in terms of this is the skill set we want to get to. We'll get to this at about 8th week or so in the semester, and then we'll spend the final 2 weeks kind of filling in some holes. But the idea here is if we all have the same understanding of where we want to go in the course, the capability that we want to build, then that becomes kind of the finish line. And now from after today until this point, which by the way, you are going to see this problem here, you're going to see it again in about 7 weeks. Up to that point in time, we're going to be just filling in things like, why did I do it that way? Why was that choice made? What if I did something different? How does that affect the outcome? Blah, blah, blah. In other words, we're filling in a bunch of holes. In front of you here is what I would call representative of the types of problems that we're going to see in the course, this being what I'd like to refer to as a machine type problem. Now as I look at my own work here, my own artwork, I see I kind of need to do a little bit of work here to kind of beef up some parts of this, if you don't mind here. I want you all to see that where I'm drawing these hash lines here, this is all solid stuff. So imagine this is some sort of a frame where this apparatus here is built into the frame, or this frame-like cavity as you see right here. We're going to see problems like this. We're going to see problems that are simpler than this when we, as we start building our capability. But this is really the pinnacle, if you will. It's a machine problem. In this particular case right here, we are contemplating the high-tech, highly important machine that is capable of crushing a can. So I am building this can crusher right here, and in doing so, and by the way, why we think of these as machines, the idea being that if this is a machine that somebody's going to use to crush a can, they're going to impart a force on that. Now, what should be fairly easy to see here is this machine consists of several links, as you see right here, a plunger, piston-like plunger, if you will, and this part right here, which is the important part, it's the handle. So the idea here, what you need to be able to see is this is a handle that ostensibly, if somebody grabs the handle and pulls up on the handle with some sort of a force. Matter of fact, the first thing I want to point out to you is the red arrow with the letter P attached to it. What's P? P, it's a name. Call it whatever the heck you want to. It's merely a force. I could have called this P, I could have called this F, I could have called this Z, I could have called this dog, cat, Jupiter, Saturn. It makes no difference whatsoever, but there's something important buried in that. When you identify a force, that force has to always have a unique name. So if I choose to call this force right here P, then some other force anywhere in this machine, I can't reuse P. I've already used that name for that particular force. If I create two forces that are not the same force, and I call them the same name, then I am guaranteeing myself that I'm not going to get the problem right. All right? So every force has to have a unique name. So back to the machine. Ostensibly, somebody's going to grab this machine, this handle right here, and they're going to apply an upward force on the handle. The amount of that force we're right now just arbitrarily calling the force P. It doesn't matter how much it just is a force. Now, if you think about how this would work, and there's a bunch of things on here that, again, as we get into the weeks ahead, we're going to define these things more elegantly, but every place you see a circle right here, and those places right there, we think of those as pins, hinge pins. Not at all unlike the hinge pins that we see on the door here. So a hinge pin merely means that whatever mechanical element is attached to it, that mechanical element can rotate about that hinged pin. So if I pull up the handle here, I see that I've got a pin right here, but that pin is also affixed by this, what's represented here is kind of like a bearing block, if you will, that is rigidly mounted into this rigid surface right here. So you can imagine this as being like bolted to a tabletop or welded down to some surface or otherwise somehow affixed to it. So if I pull up on this and this pin is affixed, then this handle here's got to rotate about that pin. As the handle rotates about the pin, what's got to happen up here? If this is fixed and we're rotating about this, if I go upwards, then this pin right here has got to move to the left, which means that this link right here has got to move to the left with it, unless of course the link is capable of being compressed, like a spring might be compressed. But throughout the course, and again, so many things we're going to talk about this morning, we're going to talk about more in detail, so don't get caught up in the details right now, but we're going to talk about later the idea that everything we're going to deal with in this course, unless we're specifically told otherwise, will be a rigid body, meaning that that rigid body has no strain to it. There's no flex in that body whatsoever. Take the tabletop right here. Listen, folks, if I climb up on that tabletop, seems to be kind of a theme, I talked about that on Thursday, right? If I climb up on that tabletop, in reality, we know that the tabletop is going to bend a little bit. It's going to make a little bit of a smile from the force that I've got standing on it, right? That's reality. However, and it becomes important to us, however, in this course, we ignore that. We ignore the fact that things actually change a little bit, they deflect a little bit, and we say, well, in rigid body mechanics, there is no deflection whatsoever. Now, utter BS. But for our intents and purposes of analysis, we say that's the case. So, this link right here is not compressible. It's not going to just squeeze itself together a little bit, which means if this is rotating on this pin right here, and we pull up on this way with this, then this piece here has got to move to the left, which means that this piece and this piece, they also have to move to the left. And the only way they're going to do that, because that's rigidly mounted there, the only way that that's going to happen is if this is moving to the left, it's going to straighten out. This is moving to the left, it's going to straighten out, which means that plunger right there has got to go down. And if that plunger is moving downward and there's a can underneath that plunger, that can's going to get crushed. So this machine, and part of what we need to be able to do as we work our way through the course is we need to be able to learn how to see how a machine works. That's one thing. But the question becomes, and I want you to think about this from the perspective of, let's say that in your future you're working for some organization and all of a sudden one day the leader comes along, the boss, whatever you want to think of that person as, and says, hey, young engineer, I want you to design a can crusher. I don't care what it looks like. Maybe it looks something like this. Maybe it's going to look like something different. Maybe this is your first idea. Maybe this is your 18th idea. Whatever it is. But I need you to design a can crusher so that if our customer pulls up on a handle with, let's say, 20 pounds of force, I need to get at least 100 pounds of force crushing on the can. So your job, the thing that's going to predicate whether or not you get your paycheck next month, is you've got to design a can crusher so that the customer, by specification, if they pull up on the handle with 20 pounds of force, they're getting at least 100 crushing the can. Here's the question for you, folks. Are you willing to bet your paycheck on, well, I'm just going to design something and hope for the best? Or do you want to have the capability of designing something and knowing that, yep, my spec says if I get 20 pounds, I got to get at least 100 here on the business end of this thing. My analysis tells me I'm going to get that. I'm guessing that you all are not in the mood to bet your paycheck on taking a wild guess, which, by the way, theme in engineering, guess what we're never paid to do? In engineering, we are never, ever, ever paid to guess. We're paid to know. So, okay, question now becomes, you came up with this idea, you sketched out this thing that you see right here, and you're thinking, okay, this probably will work, but I need to know, am I really going to get my 100 pounds of force over there on the plunger if I do apply 20 pounds over here? That right there, ladies and gentlemen, is the essence of this course. It's how do we know? What are the techniques that we need to develop? The tools that we're going to put in our toolbox so that whether it's a can crusher, whether it's a automotive system, a structural system, whether it's a robotic end effector, whatever it is, we've got the capability of analyzing forces in a system and knowing whether or not we get the forces that we want, or better yet, what the forces are so that we can manage them. Hey, let's face it, the mere fact that you might design a machine like this, which sure enough, your analysis says, yeah, if I put 20 pounds on this, I'm going to get what I want over here. No problem. The next question becomes, all right, now what are we going to build that out of to make sure it doesn't break the first time it's ever going to get used? Again, I'm guessing you're not in the mood to bet your paycheck on your design if the very first time a customer comes along and they lift up with 20 pounds, that pin there just breaks. Now they got a handle dangling, doing absolutely nothing. Your popularity in the engineering polls just took a nosedive after that one, right? So the question then becomes, how do I design it so it works and it doesn't break, doesn't fall apart? Once again, and we talked about this last Thursday, those questions are answered, but only after we know the forces within the system. So now, that brings up another question. If I'm applying 20 pounds of force to this handle right here, and I'm lifting up on the handle, the question becomes, where are the forces in the system? We know we got one right here. We know we got forces pressing down on the can, right? But where else? That's a loaded question, by the way. It's one of those, there's no wrong answer. Where else in this system might force exist? The answer, everywhere. Forces are everywhere. So, for example, I'm going to need to design that pin right there so that whatever forces exist on that pin, they're not just going to snap it. I need to design that link right there so that whatever forces act upon that link, it's not just going to buckle it or break it. I need to design all these pieces so that they can withstand the forces that develop in the system. And we talked about the other day, that means we're making a bunch of analyses on stresses within those components. The stresses provide the answers we're looking for, but we can't get stress if we don't know forces. So at the end of the day, we are ultimately going to need to know all the forces in this machine right here, and we're going to have the tools that are going to allow us to do that. But before we go that far, let's just get back to the can. Let's keep this simple for at least today. We'll get more into the details later on, but let's keep it simple for today. I want to know, if I really do apply 20 pounds of force right here, will I get my minimum 100 required right here? All right? How do we do that? I mean, where do we even start? The answer to that, folks, may surprise you a little bit. And I want to say this, and I'm not saying this to be dramatic by any stretch of the imagination. I don't want you to think I'm overselling it, but I certainly don't want you to think I'm underselling this. The key to solving this problem, and frankly, all statics problems, all engineering mechanics problems like this, the key to everything rests in our ability to draw a picture. That's it. At the end of the day, you will come to understand that success in this course is driven entirely by how good am I at drawing pictures. It's the tail that wags the dog here, ladies and gentlemen. The pictures that we're going to draw are what we call free body diagrams. Now, from physics class, You've probably heard of free body diagrams before. Most people who have taken any kind of Newtonian physics or anything like that have been exposed to free body diagrams. Draw in closely and hear me, folks. Forget everything you've been taught in physics about free body diagrams. Forget about it. I can't tell you how many people make mistakes in here, in this course, on free body diagrams, and then we'll go back and say, but that's the way my physics professor taught us how to do it. How many of you are going to be engineers when you graduate? Yes. How many of you are going to be physicists when you graduate? Okay, point made. So we're not physicists. Physicists make free body diagrams a certain way, and frankly, it's kind of the same as we do, but there's one really important thing that they miss out on. As engineers, part of our job is communicating to other people who are not engineers what we know. So a physicist might say, well, you know, you could draw a free body diagram of this handle right here by just making, for example, I'll just do it with my finger, just a line and a line like that and make it look like a elongated sideways T, and that's good enough. Okay. But if part of the engineer's job is to communicate to others what we're doing, what we know, what we're thinking, did we really communicate? If we drew a free body diagram, this thing right here, and that free body diagram looks something like this, are we really communicating what that thing there looks like? Not at all. So you see, folks, part of what we have to do is not only make the free body diagram, but it's got to convey what we're talking about. Very important, very, very important. And like I said, I don't want to oversell that, but I don't want to undersell it. I want to make sure nobody in this room right now is thinking, I don't really need to do that because I can just draw free body diagrams the way a physics professor blah, blah, blah taught me, and I'm good to go. You will not be good to go. Okay? That will not work out. So, we need to learn the art of making free body diagrams. Then the question becomes, free body diagram of what? Is there any right or any wrong in what you choose to make a free body diagram out of? The answer is there is no wrong. Meaning that, let's say you looked at this and said, I think I just want to draw a free body diagram of this handle right here and start there. You can't go wrong. It's important to understand, though, it may not lead you where you want to go, and that brings us to important principle number 2. Important principle number 2 is when you draw a free body diagram, which we are going to use, by the way, so there's a sequence here. Free body diagram leads to mathematical model leads to solution, okay? You're going to find that sometimes you will draw a free body diagram of something and it doesn't produce any fruit. It doesn't lead you where you want to go. So, okay, what do we do then? Well, option A is give up. Once again, we're engineers. We solve problems, therefore we don't give up. All it means is if you draw a free body diagram, it doesn't take you where you want to go, well, draw a free body diagram of something else. That's all. Keep drawing free body diagrams until you get where you want to go. If a free body diagram doesn't produce fruit, move on. No problem. So, for example, I might say, well, I think if I start with a free body diagram of this handle, it's going to get me somewhere, it's going to produce some fruit. As we're going to see in a minute, that's true in this case. But you might also look at it and say, well, wait a minute, I'm advanced. I want to draw a free body diagram of this handle plus that link attached together. Can I do that? Yeah, absolutely, because you can't go wrong. Could I even make a free body diagram of this handle, this link, this piece here, and that plunger attached to it? Yes, absolutely. Will that big free body diagram produce fruit? No, it will not. Not at least on the first pass, but it might on the second pass. Now you're thinking, okay, wait a minute, what are you talking about? We will find that sometimes we draw a free body diagram, it doesn't lead us to the final solution, but we save it for later because something that we might pick up in another free body diagram now adds to info for that one, and now it does produce fruit. It is not at all unusual or wrong when we're working a problem like this. It's not at all unusual or wrong to think that you might need several free body diagrams to solve the entirety of the problem. Nothing wrong with that. Nothing wrong with that. Simple stuff? Yeah, one free body diagram, good, you're done. We'll see those in like chapter 3. But when we get to the deeper stuff like this, that's not going to be the case. We're going to have multiple free body diagrams, a multiplicity of equations that are going to come together to solve the whole problem. But don't let what I just said bother you, because as you're about to see, it's really a remarkably straightforward process. As long as, and again, draw in and hear me when I say this, as long as we start in which we all accept the idea that my number one job in doing stuff like this, my number one job is get the free body diagram right. Because folks, hear me when I say this, you're going to see that free body diagramming and the process of solving these problems is a two-step process. Free body diagram and apply 3 equations to each free body diagram, where those equations are going to lead to answers about forces. Another free body diagram, 3 more equations. Another free body diagram, 3 more equations. Hear me when I say the equations are actually nothing. The equations are the same fundamental equations every time. And as with all equations, we will make mistakes on equations, right? Math mistakes, good at making them. You are too. I'm great at it. But know this, if your free body diagram is right, the equations will eventually be right too, and you'll get your solution. But if your free body diagram is wrong, you'll never have correct equations. Therefore, you'll never solve the problem. So at the end of the day, the thing that matters is the free body diagram. We're going to get really, really good in here at making free body diagrams. So now the question is, cool, how? Let's do this. Let's make, I said a moment ago that the handle was going to be, and by the way, I'm just referring to my notes here because I'm telling you folks, I just want to make sure I'm not going to forget anything. And I haven't so far. So I said a moment ago that we could do a free body diagram with just that handle, and it's going to lead to some fruit. In other words, it's going to take us somewhere of value. So the question becomes, how do I do that? All right, hear the words free body. Free body means that you are going to draw a picture of the thing that you want to be as your free body diagram, completely independent of everything else. Now that's just a long-winded way of saying draw the thing, but don't let it be attached to anything else. Don't let it be touching anything else. Well, professor, is it okay if I like show some ghost lines where it used to be attached to something? No, it's not a free body diagram if you do that. It's got to be by itself. So okay, I want to draw a free body diagram of this handle right here. Get ready for some hardcore artwork, folks. Voila. Years of art school and failing art classes led to that. There is the handle. It is by itself. It's not touching anything. You might say, but hey, professor, aren't you still showing the pins here? Well, I'm actually showing the pin holes. All right, so if I needed to like shade that in or something to make it clear that there's a hole there, I can do that. But I have drawn the handle here as an isolated body representative of what the thing actually looks like. This is the important thing I was telling you about. Again, physics professor might say to you, just draw a T shape, it's all good. No, you must draw the free body diagram to represent the mechanical element. And by the way, don't think for 2 seconds that I'm not leading you to do that for something that's going to be very important to you in a year or two. Okay? You could argue, but at the end of the day, it still works here in statics. It works fine. Yeah, but this isn't about just statics, right? So no, we want to get real good at representing visually what it is we're analyzing. So there you have it. I've done the hardcore artwork of drawing a free body isolated version of this handle right here. So now what? Well, once you draw the free body itself, there's a number of things that we need to do. And one of the first things I'm going to encourage you to always do is always start. In fact, I will say it this way. When you're drawing a free body diagram of something, before you lift your pen after drawing up the image itself, always draw a coordinate axis system. In other words, I sketch this. The very first thing I should do after that is just come somewhere and draw in a reference coordinate axis system. Of all the things you'll ever do, folks, that one's really easy. But it turns out it's really important too, brutally important, and you wouldn't even realize it until you find out why. By the way, before I forget this, let's also note that everything I'm doing right now is 2D. We're doing two-dimensional representations of three-dimensional objects. I mean, look, if we were to build this thing here in real world, then there's an X direction, there's a Y direction, and there's a Z direction, right? But for our intents and purposes here in statics, we're going to, for the first 9+ weeks of the course, we're going to keep everything in 2D world, all right? Now, that's an important thing. I want to talk about that. In your book, you'll see that every chapter of the book is segmented into, the first part will be two-dimensional statics, the second part of that chapter will be three-dimensional statics. We have a choice. The choice is that as we're going through and learning statics, we could take each chapter, spend some time on the 2D stuff, and then go and transition over to, hey, here's the 3D stuff. Then we move to the next chapter, we do the 2D stuff, and do the same thing, do that over and over again. Folks, if we had 15-week semesters like your traditional universities do, we'd probably do that all day long. But we don't have that. We've got effectively 9-ish week semesters by the time we get done with holidays and stuff like that. So we don't have a ton of time. So a choice needs to be made. The choice is, do we want to just touch upon everything all the way through the course, 2D, 3D, 2D, 3D, that kind of thing, touch upon it to say, check box, we covered everything, or are we smarter to say, let's get really good at 2D statics, because once we're really good at 2D statics, adding the third dimension is a cakewalk. Yes. We're going to choose the latter. We're going to go through this entire course learning two-dimensional statics. And then once we're there at the end of the course, we're going to spend about the last 2 days of this course where I'm going to come back and say, okay, now I want to show you how we do this in 3D. And trust me, folks, I've been down this pathway enough times to know it works out great. If you become good at 2D statics, transitioning to 3D is a nothing burger, nothing to it. So that's the play here. That's why you're seeing me do two-dimensional stuff. That's why when I do the coordinate axis system up here, it is just going to be two-dimensional, X, Y, as you see. Now, in drawing the free body diagram, I make a sketch of the object, I add the coordinate axis system, and then we come to the important, the all-important. We need to represent the forces that are associated with, and hear me when I say this, just that object. Just that object. Had I chose, just think about this, before I ever drew the handle over there, let's say that I looked at this and I said, I think I'll start my first free body diagram to be this plunger right here because, well, that's where it's crushing the can, so I need to know force on that plunger, otherwise I'm never going to know the force on the can. So I choose to draw a free body diagram of this thing over here, the plunger with the pin bearing surface on that. I draw that as an isolated body, all right? Now I start assigning force to this plunger, and I'm talking about how we assign those forces in a minute, but as I'm assigning the forces, I'm looking at this thing and saying, you know what? I got this force over here, this P, this 20 pounds, that's got to affect this somehow, so maybe I should draw a P on that too. Nope, P's over here, it's not here. The mistake to be made that y'all don't want to make, excuse me, is to assign a force to something where that force is not on that something. only put forces on things that are actually applied to that thing. In our case here, we know for a fact that force P here is indeed applied to the handle right here. So it's okay to go ahead and draw that force in exactly as it is. But remember, we have said that in our case, the specification for this is that the force P is going to be equal to 20 pounds. So I'll go ahead and add that 20 pounds to it. Let me tell you why that's really important. One of the disciplines we want to get into is when we actually know the value of a force, always write it down. I'm getting looks like, dude, duh, right? Oh, folks, you'd be amazed how many times people won't write down the value of force that once it's known. And then the next thing you know, you're 6 equations later and you're like, I can't solve this problem because I got 4 unknowns and I've only got 3 equations. What am I supposed to do? Well, you never had 4 unknowns. One of them was a known, you didn't write it down. So it's a little trap that, again, stay out of that trap. When you know the value of a force, always write that value down on your free body diagram. Don't leave it as an unknown because you don't want to be an unknown. P was drawn as an upward force here. P is drawn as an upward force right here. I'd add the 20 pounds. By the way, we'll be working a course in both English units and SI units, so sometimes we'll be using pounds. The standard unit of force in the English system is the pound. You don't need to do anything to that. It is, if it's 20 pounds, then it's 20. In the SI system, it's the Newton. All right, and we need to know things like, well, kilonewtons means thousands of newtons, meganewtons means, million newtons, and so on and so forth like that. Watch out. We will be doing, I said, we'll do both. This particular one I just chose to use pounds because I chose to use pounds. But when we do the SI system, be careful. The author of the book, as does all authors of all statics books and just about every engineering book, I think they think it's amusing when they sometimes give you that something has, and I'm talking in this case, I'm talking about weight forces, right? The weight of something. They'll give you the weight in terms of its mass, and then you have to convert that mass into an actual force. We see that in the SI system. So we'll see that from time to time. I'll talk about that as we go on. You do that in the SI system when given a mass. In the English system, you're never ever going to be given a mass in this class. So if you're given a force in pounds, you do nothing to it. It is what it is. You don't need to convert anything because it's not a mass, it's already a force. So now, we've got our free body diagram. We've got the applied force here. We've got our coordinate axis system. But we're not done with the forces. And here, ladies and gentlemen, is where the skill comes in. Okay? That free body diagram up there is not complete until we've contemplated all the other forces that may be applicable. Starting with number 1, are there any other applied forces? Any other forces that are being applied to this, extant upon this element? If the voice of common sense on your shoulder is saying, well, no, because if there are any other applied forces, they would have been on that picture right there, listen to the voice of common sense. There are no other applied forces. The 20 pounds is the only applied force, so check, that box is done. Next up, if I really had that handle in my hand right now, does that handle have any weight associated with it? Of course it does. Everything's got weight, right? Everything's got weight. Well, at least physical objects have weight. So now, what's the weight of that handle? Come on, what's the weight? You gotta be looking at me like, you didn't tell us. That's right, it wasn't specified. So here's the fantastic news, folks, the fantastic news. Throughout the entire course, unless you are told that something has a weight, we get to neglect it. The mere fact that there was nothing in this setup here that said, hey, this handle here weighs 4 pounds and that link right there weighs like 0.7 pounds and so on and so forth like that, we get to ignore all of that. Now later on, we'll see problems where we can't ignore the weight. And then we need to know how to apply that weight. Not so much how, but where. Okay, where do we apply that weight? All right, so applied forces, check, we got that already. Do we need to represent weight on this? No, because there is no weight on this one right here. But then there's the last of the forces, and these are the important ones. It is the internal forces as they apply to the problem. Let's be careful with understanding that. When I apply this weight right here, I'm sorry, this force right here, if I apply this 20 pounds, if I just pick any random spot, like right there within the handle, is there a force? Does that 20 pounds cause some kind of a force on that spot right there in the handle? Yes. Do we care? No. Couldn't care less. Now, again, next semester in solids, you will care about that. And we'll talk about that as we go along. Once we get into chapter 3, I think I'll talk a little bit about that, just so we all have a little bit of a preview of what that looks like. But right now, we couldn't care less that there is a force in the handle here, 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 here. Nobody cares. But we do care about them in certain places. And those places are, again, this that I'm telling you right now, this is the big deal that I'm telling you right now. We care about forces wherever the object used to be in contact with something. If there was contact, there must be a force. And corollary to that, if there was no contact, there cannot be a force. So you can't randomly look at this and say, gee, I don't know, it just seems like there's got to be a force right there, shouldn't there be? No, because there's nothing in contact right there. But as I pull this thing apart right here, where did I used to be in contact with something? Answer, that pin right there and that pin right there. Now arguably, well, are you also in contact with this strap here, this link? Yeah, but remember, we don't have this dimension right here, so we assume there is no contact in this Z dimension. So we would merely have contact with the pin at the top, the pin at the bottom, which means that in places where I used to have contact, these two places right here, I have to have forces shown on that free body diagram. But then the question becomes, well, what do those look like? How do I draw those forces? And again, there's some skill in this. Let me start by saying the way we're going to draw those forces is complete, unadulterated bull. We're going to draw those forces as individual point forces. In other words, forces that are applied just at one point. Arrows, exactly as you see right there. But folks, is that ever really true? No. If I sat down on this tabletop right here, I just applied force to this tabletop. Is that force really just being applied at one single point? No. It's applied over an area. There's a distribution of the force being applied over an area. In chapter 5 of this course, we're going to get into how do we deal with real life, with distribution of forces. How do we deal with that? And I'll give you the preview answer right now. It's simple. We're going to take a distributed force and turn it into a regular old arrow, because by that time, if we can convert the distributed force into its arrow equivalent, then we already know how to do all the math on the arrows. We call them point forces. We know how to do that. So we deal with distributed loads by turning them into point forces and just doing the same thing we've always done. It's not hard. But it's going to be hard if by that time we're not good at doing the math, drawing the free body diagrams and doing the math on point forces. So, takes us back to, again, what do we need to do over here? Well, the answer is we need to show then arrows in places where we used to be in contact with something. And then the next logical question becomes, how many arrows, which way do they point, and does it matter if they're going that way or that way? Some of those answers have, or some of those questions have important answers, and as you're about to see, some of them don't have important answers. There is a rule of thumb that we're going to talk about a lot a little bit later on, and that is In the face of uncertainty on where to draw arrows, always ask yourself, if that was a physical object, if it was a real physical object, and I really did have this physical object here with a pin right there, a pin going through that. If I took this physical object, let's say I detached it from everything else, but I have this pin right here. If I took this physical object and tried to move it then in the Y direction, and again, this thing has a pin going through here. There's a pin here. If I try to move this in the Y direction, if I just simply grab the handle and try to pull it up in the Y direction with a pin going through like that, would I face resistance to that motion? Sure, of course you would. So because of that, if you would face resistance to motion in a certain direction, you've got to have a force in that direction. Similarly, if I had the same pin here in this handle, and I tried to move the handle, I tried to pull it in the X direction, or Y direction, positive X or negative X, whatever, in that direction, would I once again face resistance to motion? Yes. So there would have to be an arrow in that direction as well. Now remember I said transitioning to 3D is pretty easy once we know 2D? Take a wild stab, folks. If I would face resistance to motion in the Z direction, would I have a force going in the Z direction? See? We're just adding to what we already know by that time. Now, here's a good one for you. If I had this handle pinned right there, we've already established if I try to pull it in the X direction, resistance to motion. If I try to pull it in the Y direction, resistance to motion. What if I tried to rotate the handle about this pin? Would I face resistance to motion if I tried to rotate the handle about the pin? The answer is yes, because in reality, there would have to be some level of friction on the pin, right? There's no such thing as a perfectly frictionless connection like that. So would I face resistance to rotation if I'm trying to rotate that about the pin? Yes, I would. But here's the great news. Do you remember how I said to you a little while ago that like on the last 2 days of this class, we're going to learn how to do 3D stacks on the last 2 days? On the day before that, we're going to start caring about friction, and not before then. Meaning that everything we're going to encounter until like that third to last day before the end of the course, we're going to lie to ourselves and say it's frictionless. There's no friction. So, if this pin was truly frictionless, and I try to rotate about that frictionless pin, would I face any resistance to that rotation? No. So in that case, I don't show, since there's no resistance to motion, I would not show a corresponding rotational torque about that pin. Meaning that right now, I've got enough tools that I could come over here and say, all right, I know that I would have a force in the X direction because I'd face resistance to motion that way, so I'm going to draw that in over here. Let's draw that in as a force going off in the X direction. And right there, stop before we're going a place further. I drew that arrow going in the positive X direction. Do I know right now whether or not that force is really going in the positive X direction versus the negative X direction? Do I know that? No. Do I care? Nope. We're going to find throughout that many of the forces that we're going to assign, when we don't know their directionality, we don't need to know their directionality. It's perfectly okay to take a wild guess that in this case here, that force is going that way versus going that way. And what you're going to learn and find out is that when we actually do the math and figure out what the force is, if the force's magnitude mathematically works out to be a positive number, then your guess was right. If it turns out to be a negative number, then your guess was wrong and it was really going that way. That's all. So right now, we don't have to worry about whether it's going to the right or to the left. We don't need to worry about that. The math will straighten us out on that one. But what I do need to do, though, is I need to give it a unique name. So I just created a force right here. Can't call it P. already used that, can't call it P. In this case here, it was associated with pin F, so to me it'd make a lot of logical sense to call this one maybe like F sub X, F in the X direction. You already know there's going to be an F in the Y direction coming up here in a few seconds. But I didn't have to call it that. I could have called it Flint, Flushing, whatever. You call it anything you want as long as it's unique. Now, we said that there would possibly be a force here in the Y direction as well, because there would be a resistance to motion in the Y direction. Same play. Here, I'm going to take a wild stab that force is going down that way. Do I know that it's going that way versus in the positive Y direction? Nope. Do I care? Nope. But I want to give it a name. Shall I call it Fx? Nope. Already used Fx. So how about Fy? That works. Now everybody needs to look at this and make sure that you have zero questions in your mind as to where the next forces are going to go. Where was the only other place left over here that we had contact? Everybody says top hole, right? All right, so there's going to be forces there. It is a pin. So if I detach this pin right here and I try to pull my handle in the X direction with that pin, give me a resistance to motion? Yes. If I try to move it in the Y direction, will that pin give me a resistance to motion? Yes. In fact, you may be seeing a pattern starting to develop here. When it comes to pins, we always assume there's an X force and a Y force, and then the math will tell us what's right and what's wrong. So assigning free body diagram forces to pinholes is straightforward, okay? So it's perfectly okay to, in this case, let me say I might assign a Y direction force. I'm going to call this one EY. And maybe I got an X direction force going this way, which I'm going to call EX. Once again, did I know that that one's going up? Did I know that EX is going to the left? No. Do I care? No, not really. But was there maybe a little bit of a tweak done here to anticipate something? The answer is yes. Let's never forget the words of Old Man Newton. Old Man Newton told us hundreds of years ago that for every force, for every reaction due to a force, there's an equal and opposite reaction. So if I got one X force going that way, it would make sense I got to have another one going that way. That's why I arbitrarily, when I drew this one off to the right, I arbitrarily drew this one off to the left. When I drew that one downward, I arbitrarily drew that one upward. Importantly, do I need to know that? The answer is no. I'm just intuitively thinking, it's probably going to be that way. But I could be so wrong, it's not even funny. Now, folks, as we continue thinking about the free body diagram that we just created for this, let's go through a little checklist in our mind. Did you draw the object isolated? Did you notice I got no ghost lines here? I don't have any ghost lines of that thing there, or ghost lines of that thing right there. It's completely isolated. Did you do that? Yes. Did you add a coordinate axis system? Yes. Did you include the applied forces if there are any? Yes. Did you include the weight if there is any? Yes. In this case, no, but there was no weight. And then, so very importantly, did you show forces at all places where this used to be in contact with something? The answer in this case is yes, we did. It's not a bad play at all when you're doing this to kind of mentally or with your pen maybe do a dotted line around this and say, hey, was I touching something anywhere else that I missed? And the answer is no, in this case. So that right there, ladies and gentlemen, is a complete, that is done, free body diagram. Now earlier on you heard me say that with every free body diagram you get to apply 3 equations. If you have 3 equations and only 3 unknowns, you will be able to solve for all the unknowns in that free body diagram. As it stands right now, we have 4 unknowns and 3 equations. So will this free body diagram produce fruit? The answer is yeah, but we won't get everywhere we want to go, at least as it is right now, okay? So this was a very good place to start. In fact, I will say this to you all. As you're thinking about where or what you want to choose for making your free body diagrams, remember a rule of thumb. In all problems, you at least have to free body diagram something that includes the applied forces. And you also have to at least include a free body diagram that shows the force or forces that you want. So in other words, this was a good choice for a start point because I need to free body diagram something that showed the applied force. Got it. But I'm also eventually going to need to free body diagram something that shows the force that I want, which is the force acting down on this can, the 100 or more pounds that I need to confirm whether I've got that or not. So, okay, will that free body diagram over there solve the complete problem? No. Is it a good start? Absolutely. So where do we go from here? I could go ahead and start writing some of those equations. I'm not going to just yet. I want to save that for later. But I want to do something instead. Instead of starting writing equations right now, knowing that I need to write some more free body diagrams, I want to create another free body diagram. In fact, in this instance, it wouldn't be at all a bad idea to think, okay, if I free body diagram that, then I need to start working my way towards this plunger down here. So maybe I free body diagram this thing right here. Okay, that linkage, if I follow my own rules right now to make a free body diagram, I'm going to draw the object isolated, not touching anything else. So here's the linkage. Boom, done. I need to give myself a coordinate axis system. Hey, by the way, I didn't mention it earlier on, but starting about chapter 2, and certainly later on down the road, we're going to see where sometimes rotating the coordinate axis system makes your math a lot easier. We're going to learn about that as we go along. But for now, nice and standard, nothing wrong with that. In fact, I will say 98% of everything you'll ever do in here, standard coordinate axis system gets the job done. Now, I got my object, got my coordinate axis system. Now let's go through the checklist. Are there any applied forces on this? I want to see every head in here going, nope, there are no applied forces. Why not? Because there aren't any, that's why. All right, there was an applied force down on the handle, but it's not on this linkage here. So you wouldn't magically add it in there, even though there will be times that the voice in your head is going to be screaming at you like, man, you got to show this thing somewhere. You show it where it is, not where you think it might be. So, no applied loads, check. Weight? No weight. We weren't told a thing about its weight or its mass, therefore nothing to worry about there. Forces where we used to be in contact with something? Oh yeah. But here now is something, and folks, remember I told you at the beginning of all this, I will always tell you when something is important. What I'm about to tell you is probably the most important thing I'm going to tell you after telling you that this course is all about free body diagrams. It is this. Whenever you show a force on a free body diagram where you have already defined that force on a previous free body diagram, you must use the same force names and, once again, hearing old man Newton, equal and opposite. So check this out. This point right here in which we define force EY and force EX applies to right there, which means over here I also have shown the same forces, and I got to show them in an equal, meaning they have the same name, and opposite way. So EX way over there was drawn pointing to the left. That means over here EX needs to be pointed off to the right. Over there EY is pointing upwards, meaning here it's got to be pointing downwards. Now, I will warn you, not that it's going to change anything, don't let the ink in your notes get too dry on this, because even though I'm showing you how we're doing this, I'm showing you the right way, I'm going to show you a better way in just a few seconds. Just want you to know that. So, okay, fine. I got EX and EY, which I have already defined, drawn in the opposite direction. Folks, the number one cause of mistakes in this course and anything beyond this course when it comes to force analysis, the number one cause is you'll forget to make it draw in the opposite direction. If you drew, for example, EY going up over there and you draw EY going up over here, your math is automatically wrong. You'll never get it right. Which takes us back to, this is why getting the free body diagram right is so important. Now I got a pin over here. We already know that pinholes we just represent for the general X and Y force. Here, now this happens to be pin D, right? So let's just arbitrarily, let's call this force here, we'll call this one dx, and we'll call this one here dy. And if we do the check boxes here, we drew the object, we included a coordinate axis system. There is nothing, there's no ghost lines or anything goofy like that. And we've got no weight, no applied forces, and we got forces at the only places where this used to be in contact with something. Done. So now, let's count things up. In this case here, I get more equations of equilibrium. So let's see. I had 4 unknowns over there. I got 2 of those forces here, so I've already counted for them. And I got 2 more unknowns right here. So now I got a grand total of 6 unknowns, and I have a grand total also of 6 equations. So as it stands right now, I actually could use my equations to solve for all these forces, and I would know the force in dy and dx. Good news, I'm moving in the right direction now, right? But I said I was going to show you something, and I'm not going to prove this until chapter 2 at the very earliest. But this particular element right here is a special kind of a mechanical structural element that we call a two-force member. And again, I'm not going to prove why this is the case. That's a little bit beyond the scope of where we're at today. But a two-force member is any structural element that, number 1, has no weight, number 2, has no applied forces, and number 3, has a grand total of only 2 places in which it was in contact with something, and both of those places have to be pins. Frictionless pins, by the way. In that case, again, structural element, check. No applied forces, check. No weight, check. And a grand total of 2 pinholes, check. That's a two-force member. When you have a two-force member, and I'm going to redraw this free body diagram over here. That, by the way, that's a legitimate free body diagram, but so is this one. When you have a two-force member, yeah, these should be rounded a little bit better than that. Art's not my thing, by the way. When you have a two-force member, it turns out, and again, I'm doing this completely without proof, completely, that there are only 2 forces existing in this member, and they must fall along a line that passes through the center of the 2 pinholes. So if I draw a line that passes through the center of these 2 pinholes here, the forces on this member must fall on that line. In this case here, the force on this is going to be represented then as a single force here and a single force here. Now the question becomes, and again, that's on that line connecting those 2 pins, which, by the way, creates something kind of unique. Check this out. Let's say that I had a two-force member that looked like the following. So check this out. Structural element, no weight, no applied forces, grand total of 2 pinholes. That's a two-force member. Where are the forces? They fall on the line drawn between the 2 pinholes. So 1 force here, 1 force there. Done. Y'all are going to find out here as we go along. You have no better friend in statics than a two-force member. When you see two-force members in your problems, they simplify things like crazy. So you will get into the habit eventually of, even before you start a problem, looking at it and saying, where are my two-force members? In this particular problem, by the way, we have 3 of them. There's a two-force member, there's a two-force member, and there's a two-force member. We didn't know it before we went into it, but those 3 things make this problem a boatload easier. So now the question becomes, oh, and just to put an end point on that thing right there. This tells us that when it comes to two-force members, the shape of the member is completely irrelevant. It can be any shape we want, anything. What matters is no applied loads, weightless, 2 pins. That's it. That's it. But now we go back to our original one over here. Now the question becomes, we got these forces here. You may have noticed that I purposefully left the arrowheads off. Now here's an example of sometimes we know the force, direction, and sometimes we don't. What's important is most of the time it doesn't matter because the math will straighten us out. This is one of those times. But the more we do this, the more experience we gain, the more we can look at something and say to ourselves, do I know the directionality here? Or better yet, do I think I know the directionality? In this case here, here's something to contemplate. When I lift up on this handle, the force here at pin E is pushing into this piece right here. As a result, it's compressing this piece. If this force from the handle is pushing that way, and Newton's law says I have to have equal and, what was that word again? Opposite reactions. If this force is pushing this way, then the force pushing back on it's got to be going the opposite way. So it would make sense for this force here then to be going in that direction. It's opposing the force that's pushing on it. And if I drew that arrowhead that way to the right, again, equal and opposite, what direction must this one be? To the left. So all right, so there's that. Now, what name should I call it? Well, here's where this gets interesting. I could still use like EX if I want to, DX if I want to. I no longer have the Y forces, so you could do that. Or maybe we're going to give this whole thing a little bit of a facelift and give it a new name. Why don't we call these forces here, since these belong to the element defined by pins D and pins E, why don't we call this force here DE? Let's call this force DE. And now, let's get rid of this free body diagram. We're not going to want it anymore. And now, if I've got force DE here, equal and opposite world again. If I got force DE going to the right over here, wouldn't it be true that the force here on this pin is no longer EX and EY? Isn't it true that this force here now simply becomes the equal and opposite version of that DE over there? So what I've got now is force DE here going off to the left. DE opposed by DE in the 2 force member. Now, remember I said a few minutes ago, you'll get used to looking for 2 force members because they make your life so much easier. Check this out. When we utilized the 2 force member of this piece right here, now we're down to only 3 unknowns over here. And I got 3 equations, which means I can solve all 3 of those unknowns and move through this problem. But it gets better than that. By the time we're done, you're going to see that you actually only need 1 equation, because at the end of the day, this is the only one we really care about. Can we figure out what fx is? Can we figure out what fy is? Yes. But if we don't care about them, do we need to? No. So we'll see that in a minute. But I want to continue on building free body diagrams. Good discipline here, folks, is to continue building free body diagrams first and then solve the math later. So, okay, where am I at? Well, I've done a free body diagram with the handle. I've done a free body diagram with that linkage. Still want to get myself down here. I'm going to propose that we draw the free body diagram now of that pin. Now, this takes us to an important concept. Is there anything we cannot draw a free body diagram of? The answer is there is nothing that we can't draw a free body diagram of. We can draw a free body diagram of a single piece within a piece, of any combination of pieces connected together, of the whole thing, as long as it's all free and isolated. In fact, we will learn eventually that we can even draw a free body diagram of a single molecule or collection of molecules within the object and apply stresses at the molecular level, or forces at the molecular level. That's called continuum mechanics. Fun course, by the way. there's nothing we can't draw a free body diagram of. So in this situation here where I'm saying, hey, let's do a free body diagram of that pin, let's do that. So now I'm going to do a free body diagram of pin, what is that, pin D? Yeah. So pin D, that's my free body diagram right there. The artwork, oh, that was hard, I drew a circle. All right, now I'm done with that. So now, does that pin have any weight? Nope. Does it have any applied forces? Nope. Should I use a coordinate axis system? Well, I've already drawn one, so I'll just stick with that one right there. Got that. But what about the forces now? Well, we know that this DE right here, that pin and that force are the same. So I got to draw an equal and opposite version of that. So here on that pin, I'm going to draw my DE force going back this way. So drawn to the right here, drawn to the left here, equal and opposite. I also am articulating with two force members CD right here, and I don't even need to draw a free body diagram of what that looks like. That's going to be a single force going along the line drawn between those two pins. So as we'll see later on and get good at it later on, we will have a force going up this way here called CD. I am also articulating with two force member BD right here. So I will have two force member BD going down like so. It is worth noting that I've got some angle information here, so I'm going to toss that angle information in. By the way, I don't have to do this on my free body diagram, I just choose to. So in this case here, throw in that this is a 67-degree angle here and a 78-degree angle here as is given to us in the original. Now go through your mental checklist. Did you draw a sketch of the object isolated? Yep. Coordinate axis system? Yep. Applied forces? There weren't any. Weight? There was none. Forces representing things that used to be attached to it or touching it? Yep, they're all there. So now that one's done. Now and lastly, folks, as I think about this, once I solve this free body diagram right here, I'm going to know force BD. When I know force BD, I'm going to know the force right there on that pin. So now I'm going to draw a free body diagram. To finish this off, I'm going to draw a free body diagram of my plunger. And the plunger, in this case, I'm going to include the plunger and the bearing surface. If I've drawn BD downward this way, I need to have equal and opposite here. It's going to be going upwards this way. So, and again, I'm going to use my usual XY axis system. So I will have BD going up like so. If this is 67 degrees right here, then this angle right here also has to be 67 degrees. I am also going to have a force that's being applied to the can. So I'm going to show that force here as being a single force going downward on the can. The only question that remains is, was I really in contact with this side here and this side right here? And if so, well, what does that look like? Well, we don't really know for sure. In this particular instance, we're not positive, but it turns out it's not going to matter. Let's assume that we really do have some contact with that, but at the same time, we said all surfaces are frictionless, right? So if this surface here has no friction on it, then would I have resistance to motion in this direction? No. But if I tried to move my plunger this way, would I resist motion? Sure. So it would be okay in this case to show a free body diagram, show like maybe some force here, I'll call it, I don't know, call it A1 here, and an opposite version, we'll call it A2, or I can use A1 again, doesn't matter. No, it can't be the same. Sorry, I broke my own rule. A2, call it that. But now, again, check the checklist here. Sketch. Did you sketch what you are drawing? Yep. Isolated? Yep. Coordinate axis system? Yep. Weight? There's no weight. Applied forces? No. But every place I used to be in contact with something, I used to be in contact with the pin here. I've showed the force on that one. By the way, if I needed to, I could show you, we could all draw a free body diagram of this to see that the BD force carries through, but it does. I've contemplated contact here, here, and all importantly, I finally have the force on my can. The thing that I've been looking for. But step back and take a breath of air here, folks, or at least that's what I'm about to do. And look at what we just done right here. We have spent the entire morning so far on this problem doing nothing more than drawing free body diagrams. Why? Because the free body diagram is everything. Until the free body diagram is right, you can't possibly solve the problem. But now we got our free body diagrams. Let's go to work on the equations. The equations that we're going to use over and over again are called the equations of equilibrium. And they're really simple as they can possibly be. The first equation of equilibrium says that on any free body diagram, if I sum up all the forces in the x direction, those forces have to add up to 0. The second one says if I sum up all the forces in the y direction, those forces have to add up to 0. The third one says if I sum up all the rotational torques, then those rotational torques, we call them moments, have to be equal to 0. 3 equations, and they all are equal to 0. I can apply those equations here, and those 3 equations will solve those 3 unknowns. I can come over here, and I can apply those equations. Now, for reasons that will become clear in a week or two, we only get 2 of them this time. But if I sum forces in the x direction and sum forces in the y direction and set them equal to 0, I'm going to solve for these unknowns. I can then come over here and apply my equations again, and I'm going to get the thing I want. But they're the same equations every time. Summing forces in the x direction, they add up to 0. Summing forces in the y direction, they add up to 0. Summing forces rotationally, and there's some detail on that one. We'll get into detail in a second. That one's a little bit trickier, but they all add up to 0. So let's see it in action. If I come over here and I sum up my forces now in the x direction, I am going to have, first of all, let's rule out the ones that aren't in the picture. The 20 pounds right here is a purely y-directional force. F sub y is a purely y-directional force. Therefore, it doesn't belong in the x equation. This, by the way, folks, is why at the beginning of all this, remember I said it's so important to give yourself a coordinate axis system. Without the coordinate axis system, how do you know what's a y force and what's an x force? You don't. But here, I've got fx going in the positive x direction, so I'll write it as positive. So fx minus dE. So if that's an x force, that's an x force. That's the only 2 x forces I've got. It's equal to 0. 1 done. Now I'll sum forces in the y direction. In this case, I'm going to have 20 in the positive y direction. Fy here is going in the negative y direction according to the way we define it, so minus Fy. And that's equal to 0. Those are the only 2 y forces we've got. So as it stands right now, think about this. If you wanted to, you could go ahead and solve this one right here. Right now, we know that that force right there, Fy, has got to be equal to 20 pounds. But even more importantly, if you solve this for Fy, we're going to move this to the opposite side of the equal sign, which makes it positive. We'll have positive Fy equals 20. That means that the assumption we made about the directionality of this was correct. On the other hand, if we solve this and got a negative 20, that merely means that what we thought was going downward was actually going upward. That's all. No big deal. Now, right now, I can't solve for this one. I got 2 unknowns and only 1 equation, but I have that rotational equation left. Now, this is a moment equation. And as I said a minute ago, this one is busier. All right, there's some things we need to understand. We're going to spend some considerable amount of time understanding how to write a moment equation. I'm going to show you what it looks like without a lot of detail. We'll get into the detail later. But in this case here, I'm going to sum my moments, and I need to pick a spot anywhere on the diagram, or technically anywhere off the diagram, that I want to sum my moments about. And as we're going to learn later on, there are smart places. First of all, there's no wrong places, but there are smarter places than other places. In this case here, I'm going to choose to sum my moments about this point right here, point F. And I'll show you why in just a second. some moments about point F, and I need to do something here, and we're going to do this every time in this course. When we start to write a moment equation, we're always going to add this little symbol in here, which is an arrow drawn in the, I've got to draw this right in front of you here, in the counterclockwise direction, because we're going to remind ourselves that any moment that causes counterclockwise rotation is a positive moment. When it comes to coordinates over there, we know positive x is that way. We know positive y is that way. But is this a positive moment or is this a positive moment? Conventionally speaking, throughout the course, counterclockwise is positive, clockwise is negative. So now, summing my moments about point F. Here's what you need to know just to get us past where we're at today. A moment is, by definition, a force times a distance. The distance is a unique distance. It's the shortest distance between the moment center, i.e. the point about which you're taking the moment, and the line of action of the force, the shortest distance. It can't be any old distance, it's got to be the shortest distance. But if you think about this, if D represents the distance from the moment center to the line of action of the force, if this force here, Fx, is passing right through the moment center itself, then what's the distance between the moment center and its line of action? 0, there is no distance. It passes through it. If Fy is passing through the moment center, its line of action passes through the moment center, no distance. So Fx and Fy, the D value is 0, which means they're not going to end up in this equation. They go away. Good. So now, we're left with the following. Look at force DE right here, the way that DE was drawn. The way that DE is drawn, if you think about how this would cause rotation about that point right there, in what will become more and more apparent in time, this force here is causing a counterclockwise rotation about this point right here. You can almost think of it as like, imagine this is a real arrow, you tie a string to the arrow, and you let the arrow fly. If you let the arrow fly, the string's going to constrain, it's going to cause it to wrap around here in a counterclockwise sense. Therefore, because of the fact that it's counterclockwise, and our convention says counterclockwise is positive, then based on that, that's going to be a positive force. So I'm going to have DE, which is my force, times now the distance between here and the line of action, which if we go way back over here, we ignored it from the beginning, the distance between here and the line of action of that force is 8 inches. So I'm going to have DE times 8 inches here. And that takes care of that one. Now, to, again, the same point, and we see the 20-pound force here. The 20-pound force here is going to be causing a counterclockwise rotation as well, so it's going to be positive, so plus 20. And now I need a distance here. That distance from our line of action, or I'm sorry, from our moment center over to the line of action of this force. And an important principle here, ladies and gentlemen, lines of action of forces go infinitely in either direction. So the line of action of P goes infinitely that way, infinitely that way. So this distance from here over to here is the distance I want, which just happens to be given to us as 30 pounds, or 30 inches. All right. And again, we took care of that force, that force. These two forces down here are not going to show up in the moment equation. I mean, we can write them in there, but D is equal to 0, so what's the point, right? So now, that's the completion of our moment equation, and moments have to add up to, again, 0. So let's set this equal to 0. Now, with that, we can solve for the value of DE. In fact, just doing the algebra on this one, when we take this 20 times 30, which is 600, we're going to slide it over to the other side of the equal sign, it's going to become negative. We're going to find out that DE is equal to minus 600 divided by the 8 inches here, which is going to work out to be minus 75 pounds. And if DE is equal to negative 75 pounds, then that means that negative 75 here becomes positive 75, slide to the other side of the equal sign. that's going to be negative 75 pounds, which means we know that Fx is equal to 75, but the assumption that it was going that way was incorrect. It's actually going the other way. No big deal. We can fix that all day long. But more importantly is this, and isn't this funny? So if you think about this, when we set ourselves up to do the forces over here, we went through a mental exercise that said, well, gee, if DE is pushing this way, then this should be going back this way, and we should have our directionality right. But our math told us the directionality was actually incorrect. Now, why is that? The answer, folks, went back to how we drew the free body diagram. Again, don't freak out about this because the math just fixed a problem for us. It's not bad, it just fixed a problem. But what happened was this. We drew this as though it was a force being applied. What's drawn on your free body diagram is actually always meant to be the reaction force. So even though the force was applied this way, the reaction was actually going this way. And our math just confirmed that. That's why you don't have to worry so much about directionality on free body diagrams. Let the math guide you to the right direction. But now we come to an important question. Once we know that a force was drawn incorrectly, should we fix the forces on our free body diagram or just carry the negative numbers throughout? The answer is yes and yes, meaning that either one is valid. I've preached this for years now, folks. What you want to do is find the thing that resonates with you, that you feel comfortable about, and get very good at that. So for example, if you're the person that says, you know what, I just feel better if I got all my arrows going in the right direction, I'll go fix my free body diagrams, do it. Do it all day long, no problem. If on the other hand, you're the person that's like, you know, I'm afraid I'm gonna miss one if I do that, then I'm gonna kind of screw myself up, I'll just carry the negative 75 throughout, that works too. Either one. I tend to like to just carry the negatives through myself, right? But on a problem like this, I can go either way. It doesn't really matter a whole lot. So I'll tell you what, let's do it and let's correct these. So in this case here, again, I don't have to do it this way. I'm choosing to do it this way. I'm going to redraw my arrow here so that this one's going this way. This is now DE going that way. And importantly, we already know it's 75 pounds. If I drew DE going that way here, then DE has to be drawn the other way over here. So I'm going to draw the arrow now going in like that. And again, we have this DE, but we already know it's 75 pounds. Now, folks, in the apex of I don't need to do this, but I am going to do it anyway, look, the same logic that told us that this arrow here was going out because the member here was in compression, right? The same logic that said the arrow should be going out, and then we found out it's really going inboard. We had the same logic going on here. So CD, we know that's in compression. We drew the arrow away. Because it's in compression, it would have actually been correct to draw the arrow going inboard like that. So I'm going to do that. And the same thing here for BD. I don't need to do this, but again, this is just kind of correcting it as I go along. And if BD is going up that way, then BD has got to be going down this way. And folks, you remember I said that we draw the forces on the free body diagram not as they're applied, but as they're reacting? It was very natural for us to think that the can force was being applied to the can right here, but the reaction is pushing back on the cylinder. So this arrowhead here is actually going this way, and our math is going to prove that. I did not need to correct that. The math would have done it for me. But again, I made the choice to go ahead and fix all this first versus just carry through the negatives, which would have got me to the same place either way. But now, with that, I applied my 3 equations of equilibrium over here. I changed this directionality here. I just want to make a little note here to myself that I changed this. And the reason I'm making that note is because I might look back at this and say, wait a minute, I got a negative 75 here. Shouldn't that be going the other way? No, right? That's another reason I'm a little hesitant to make those changes, but again, did. Now, with that, I'm done with that free body diagram. But now I can come over here and look at this free body diagram. Somehow I got rid of the arrowhead here. Look at that free body diagram. I now have two unknowns, and I got two equations of equilibrium. I said I only had two this time. Why? Because the moment equation, if you look at this, the line of action of all these forces passes through one point, which means the distances for all of them would be 0. There is no moment equation on this one. But I have two force equations. So I can sum forces now in the x direction. So if I sum forces in x, I'm going to have this force here, which is going in the negative x direction, so therefore it's negative 75. This force BD, and I'm going to start doing a little math magic here, folks, so don't get too caught up in this. But the x component of BD, because we're going to do this in a lot of detail later, the x component of BD is going to be force BD times the cosine of the 67-degree angle, so plus BD cosine 67. And then this one here, also tending towards the positive x direction, so plus CD times the cosine of 78. And that force equation has to add up to 0. Can't solve it, we move to the next. If I sum forces now in the y direction, I'm going to have, now first of all, DE is a purely x directional force, so nothing there. But I've got this one, this force BD, which is tending towards the positive y direction, so it's going to be BD times the sine of 67 degrees. This force CD here is tending towards the negative y direction, so minus CD times, in this case, the sine of 78. And that has to add up to 0. So now I got two equations, two unknowns. I can solve those. I can solve them algebraically. I can plug them into an equation solver, whatever. What I can do here, because BD is the only one that I care about, at the end of the day, if I figure out what BD is, then I get to solve my problem here. So let's do this. Let's solve for CD as a function of BD. So if I solve this one here, I'm going to find that CD is equal to BD sine 67 divided by the sine of 78. And with that, I can take this now and plug it in right here. So this equation that I'm about to rewrite way the heck over here is going to be the following. I'm going to have BD cosine 67 plus BD sine 67 cosine 78 divided by sine of 78. That whole thing has got to be equal to, when I take this negative 75 slide over the other side, the equal sign is going to become positive 75. Voila, done. Now folks, I don't have the numbers, yeah, actually I do have the numbers right in front of me here. If I solve that right now for BD, which I can, and I'm not going to waste your time on the algebra for this one, but if I solve this for BD, I'm going to find that BD ends up being equal to 128 pounds. So I know that BD is equal to 128 pounds. What's left now is the force on the can. Now that I know that this BD here, and again, remember a principle, once we know the value of something, we don't leave it as an unknown. We know that BD is equal to 128 pounds right here. And that came out to be a positive number, so our directionality is correct at this point. Directionality is correct. Now, if I want the force on the can, I need one equation. Because the force on the can is a purely y-directional force. So therefore, from this, if I sum up my forces in the y direction, note, we drew A2, we drew A1 to be purely x-directional forces. They don't show up here. That's why I said earlier on, it's going to turn out they don't matter. But in this case here, F can is going in the positive y direction, so I got F can. And now BD here is tending towards the minus y direction, so that's going to be minus BD times, in this case here, the y component is going to be associated with a sine of 67 degrees. So minus BD sine 67, and that's going to be equal to 0. And with that, I already know that BD was equal to 128. And if I plug that in, take 128 times the sine of 67, I'm going to end up with about 118 pounds. This is going to lead me to find that my force of my can is 118 pounds. And if y'all remember, the goal going into this was we wanted to make sure that our design, if a user did in fact apply 20 pounds to the handle, would they get at least 100 pounds crushing on the can? And they got 118. We're there. I just showed you the end. I showed you where we're going. This is the intent of this kind of analysis, to be able to take a machine like this and work our way through and analyze to find a force that we want. There are so many gaps in what we just went through, folks. We're going to spend the next 5-6 weeks just filling in those blanks. But this is where we're heading. But if there's a takeaway to be had here as we wrap up the morning, and we are done, if there's a takeaway to be had here, it is this. Think about what you just saw. You saw nothing more than a lot of time spent getting a picture right. Then once the picture was right, we just kept applying the same equations of equilibrium until we got what we wanted. The equations of equilibrium, folks, anybody can do that. The skill that we're all going to build is drawing pictures. That's it. Any questions, folks? Anybody? Fantastic. Again, if you weren't here with us the other day, last Thursday, pop on by, say hello. Otherwise, I'll see you all again on Thursday. We'll pick it up from here, starting chapter 1.